Let's try some vector word problems. A remote-controlled toy car is running at its top speed of 20 kilometers per hour when you place it on a treadmill set to 12 kilometers per hour. What will be the velocity of the car relative to the floor? Assume the car is driving forwards on the treadmill. Okay, so let's try to visualize what's going on here. So here's your treadmill surface, right? We'll say that to the right is facing forwards. So the surface of this treadmill is moving backwards. It's moving to the left. And the car that's placed on the treadmill, I'll draw the car here for us. Very nice drawing, like that. This car is moving to the right. It's moving forwards. Now the speed of this car as it moves forwards is 20 kilometers per hour. Right? That's how fast this car can go. And the treadmill surface is moving backwards, so to the left, 12 kilometers per hour. Now, if this car was just on the floor and it zipped by at 20 kilometers per hour, you could look at it and say, yeah, it's going 20 kilometers per hour. But because the surface that it's driving on is going in the opposite direction, relative to us, if we're standing on the floor observing this, it's not actually going to be driving 20 kilometers per hour. And in a case like this, it might be intuitive to you. You might be able to figure out how fast it appears to be going, and that's what we're being asked for, right? What's the velocity of the car relative to the floor? Not relative to the treadmill surface, relative to the floor that the treadmill is sitting on. So if I'm standing over here on the floor and I'm looking at the car, right? I'm looking at what's going on. How fast does the car appear to be moving? It doesn't appear to be moving 20 kilometers per hour because the surface that the car is on is moving in the opposite direction. So when I'm looking at it, it's only going to appear to be moving 8 kilometers per hour. How do I know that? Well, I know that because you can subtract these two values to figure out the car's speed relative to us. So how do we do this with vectors? Well, we can show that we have a vector of 20 kilometers per hour moving in the right direction. And we can add a vector that represents the velocity of the treadmill surface. It's moving to the left. And how do we add vectors together? We go tip to tail, right? So we're now here. I'm now going to move to the left by 12 kilometers per hour. That's my second vector. And now you end up here. So now what's the resulting vector? Well, the resultant is, we got to look at where we started, where we ended up. That is your resulting vector. If this is a distance of 20 and we go backwards a distance of 12, what we've done is gone forwards by 8 kilometers per hour. So that vector represents the speed of the car relative to the floor, relative to us if we were standing on the floor observing this. Okay, so vectors can be used even though these aren't physical dimensions. They're not physical distances like we've seen in previous examples. They are instead speeds. You can still subtract them and add them as though you would with vectors that represent distances in order to figure out what the resultant velocity would be. Right? So remember, when you add vectors, you have a vector like this, a vector like this. You look at where you start and you look at where you end and you connect those dots together like this. In this case, it's the same thing. We have that white vector, 20 kilometers per hour, the yellow vector, 12 kilometers per hour in the opposite direction. And so that yellow vector ends up lying directly on top of the white vector. And the difference is, right, you look at where you started, where you ended up, it's this 8 kilometers per hour vector. All these vectors are lying on the same line, right, because we're only looking at our speeds in that same direction, right? So that's a relatively simple example, but the answer would be 8 kilometers per hour, and it would be 8 kilometers per hour forward or 8 kilometers per hour to the right. Remember, you always want to indicate your direction because it's possible that if this speed here, the speed of the treadmill, was greater than the speed that the car can travel, then the car wouldn't be moving forwards. It would actually be moving backwards, right? The car has to have a top speed that is faster than the speed that the treadmill is moving in order for it to move forwards, right? Basically, looking at these two numbers, whichever one is greater is going to indicate which direction the car is moving in. Hopefully that makes sense. Okay, let's look at another example. The airspeed of an airplane is 800 kilometers per hour, north 30 degrees east. If the wind is moving at 85 kilometers per hour, south 40 degrees west, what is the velocity of the airplane relative to the ground? So there's a lot of terms in here that we need to talk about. So when we talk about airspeed of an airplane, what that is the speed the airplane is traveling relative to the air that it's in. So that's different than the velocity of the airplane relative to the ground, which is what we're looking for, right? So if you have an airplane up here in the sky and it's traveling this way and you're on the ground over here, right? You're on the ground and you're looking at that airplane, right? You're viewing it. You can see that, okay, the airplane, goes from here to here, that distance in a certain amount of time. You can divide that distance by that time and figure out, oh, that's what its ground speed is. That's the speed relative to the ground. But what we're given initially is not the speed relative to the ground, it's the speed relative to the air. And the reason that matters is because the air can be moving, right? The air doesn't stay in one place the way that the ground does. And that's what we call wind, right? Wind is when the air moves. So the speed of the plane relative to the air that it's in is going to be that 800 kilometers per hour. So what we can do is we can use these two things together, the airspeed and the wind speed. When you combine those two, that's when you get the velocity of the plane relative to the ground, right? Because both the air is moving and the plane is moving within the air. You have to combine both of those together to figure out what its actual velocity is relative to the ground. So let's add those two vectors together. We'll start with the 800 kilometers per hour north 30 degrees east. I'm going to make our little cardinal directions here. So north, east, south, west. North 30 degrees east means that we are in this direction here. You look north, you rotate 30 degrees to the east, and that's where your vector is. And this is a vector of 800 kilometers per hour. And again, this is not a distance, right? It's a velocity. You can add the velocity vectors together in order to figure out what its actual relative velocity is, what the resultant velocity is. So that's our first vector. Now we want to add the second vector to it. So I'll make another set of cardinal directions here, and I'll use a different color. So we have our north, east, south, west. Now, south 40 degrees west means that you're going to be something like this. You look south, you turn 40 degrees to the west, and that's where your vector is. And this vector is 85 kilometers per hour. It's getting a little crowded, so I'm not going to write in the units there, but you get the idea. Okay. Now the resultant vector, right, the answer we have is going to be from where we started to where we ended up. So this will be your resultant vector, and this is not a perfectly vertical line. It just looks like that in my sketch. My sketch is not exactly to scale, but that's the resultant vector that we're looking for. So of course you can try to solve this question using trigonometry, right, trying to figure out what all the angles are inside of here, looking at the lengths and trying to come up with what you think this length should be. You can absolutely do it that way. You can also simply look at the x and y components, and that's how I'm going to try to figure this out. Okay, so in the x direction, right, in the horizontal direction, let's look at all the components we have of that initial vector, that white vector, the 800 kilometers per hour. What is the x component of that vector? Right? If that vector here, if you were to make x and y components to it, what would those two dimensions be if that vector was our hypotenuse? Well, you would simply take 800 multiplied by sine of 30 degrees, and this value would give you the x component. Now, remember, we like to say that cos is what we usually use for x, but that's if we're dealing with this angle here. And you can do that, right? This angle here is 60 degrees, right? Because this one is 30. 30 and 60 make 90, so this one has to be 60. So if you're going to use cos, you would use that 60 degrees to figure out what this x direction is, and you could absolutely do that, right? You can say 800 cos of 60 degrees instead, if that makes it easier for you, right? If that makes it easier for you to imagine this triangle, you put the 60 there, you say 800 cos 60, that gives you this dimension here. You can absolutely do that, okay? Now, that's the x component for that first vector. We want to add to that the x component for the yellow vector, the 85 kilometers per hour. And what we notice is that that vector in the x direction is going the opposite direction. It's going to the left, whereas the white vector went to the right, which means we're going to have to subtract the x component for this vector. We subtract 85 multiplied by cos of, what angle do we use? Well, this angle here is 40 degrees. So if you want to use this angle in here to imagine this right angle triangle, this angle in here would be 50 degrees, right? This is 40, this would be 50. So we can say 85 cos 50 degrees. Again, if you wanted to use cos for both of these, you got to make sure you're using the right angle. But again, it doesn't matter. You could use sine 30 and sine 40. You'll get the same answer as if you use cos 60 and cos 50. Now, those are the x components of each one. We've combined them together. If you add those up, what you'll get is the total x component for the resultant vector. And if you do that, you get about 345.4 kilometers per hour. I'm rounding that to 1 decimal place. I think that's good enough. Now, notice that your answer is positive, right? That means that this resultant vector is going to the right. Again, this obviously is not to scale. If this is a length of 800 and this is a length of 85, clearly this is not to scale. A more to scale version would look something like this, right? Where this is now your resultant vector here. So that's a more to scale version of this. So it makes sense that this is going very far to the right, okay? Hopefully that makes sense. Now let's look at the y component. For the y component, you simply use sine in place of cos in each of these, right, to figure out what those vertical components are. For the first one, we'll have 800 sine of 60 degrees, and it's still positive because it's moving to the right, so the x component's positive, but it's also moving up, so the y component should also be positive. For the yellow vector, the 85, it's moving to the left, which was why the horizontal component was negative, but it's also going down, right? So the y component should also be negative. So I'll say negative 85 sine 50 degrees. So just because this is negative doesn't mean that this is negative. And just because this is positive doesn't mean this is positive. It just happens to be that way in this question. Okay, so pay attention to the directions. In fact, in each of these equations that you're making here, you should define your horizontal components. You should say that to the right is positive. And for your vertical components, you should be saying that up is positive. Now, this is not necessary. You can say the opposite. You can say the left is positive or down is positive. It's up to you, but this is most typical. It's good practice to stay consistent, and I like doing it this way. Now, when you add these two together, you should get an answer of 627.7 kilometers per hour. So these are the components we get. So if you take these two components and you say, okay, 345.4 to the right and 627.7 vertically up, then what is the resultant vector that you get? Well, you can simply use Pythagorean theorem, right? This is a 90-degree triangle. We'll use the Pythagorean theorem to figure out the magnitude of that resultant vector. So we're going to call this vector r. The magnitude of vector r will equal the square root of 345.4 squared plus 627.7 squared, just like that. And I'm just going to round my answer to the nearest whole number. I'm going to say 716 kilometers per hour. Really what you should do though is use the exact values here and here because they're going to be squared, added, square rooted. There's a lot of opportunity to lose your accuracy if you're using those rounded numbers. So try to use the exact values there if you can. I'm just going to round it off though. I think for our purposes this is fine. So this will be the magnitude of your resultant vector. Now again, we needed the velocity, which means that we have to include a direction. So I'm going to find out what this angle is right here, and we'll be able to use that for our final answer. So how do we find that angle? Well, we have our opposite and adjacent sides. So I say we use tan. So if this is angle theta, I can say tan of angle theta is equal to opposite over adjacent. So theta is equal to the tan inverse of this, right? So you want to type into your calculator tan inverse of this fraction, right? Put it in there. And as an answer, you should get 61.17 degrees, or I'm just going to round this to 61 degrees. So for your final answer, we can say that the resultant vector r is equal to 716 kilometers per hour. And then what's the direction? This is 61 degrees. So we would say if that's 61 degrees, that this angle here would be 29 degrees, right? Because they have to add up to 90. And I would use that because then you can say north 29 degrees east. So north 29 degrees east, like that. And that would be my answer, right? That is your vector r. That is the relative ground velocity of the plane. Now, let's do another example. So in this case, we have forces of 12 newtons and 20 newtons applied to a box as shown below. So we have a nice diagram here, which is always good. Question is, what is the total resultant force being applied to the box, and what is the total horizontal force being applied? So we've already seen examples where our vectors represent physical distances, dimensions. We've had examples where they represent velocities, right, or speeds in different directions. And now we're seeing that you can also use vectors to add forces together. So the first part of this question is saying, what's the total resultant force being applied to the box? Well, we can make a prediction that because this force is horizontal and this force is down, that the resultant force you're going to get is kind of in, this direction, right? It's kind of between these two vectors. You could kind of say it's something like this, all right? That's my prediction anyway. So let's actually look at this. We can break down each of these vectors into their x and y components if we want to do it that way. We'll look at that first vector. We'll break it into the horizontal components here, and I'm going to say that to the right is positive again. Again, that's a nice way to do it. So we'll say that our x component of this vector here is equal to 20 multiplied by cos of, and then what angle would we use? Well, if this is 30 degrees, then this angle in here must be 60 degrees, right? So I'll say 20 cos 60, and I will add to that the x component of this vector. This vector is horizontal, so it's actually all in the x direction, so it would just be 12 newtons. And I can add these two things together. Again, you don't have to go through this process with this vector because this vector is 100% in the x direction. It has no vertical component to it. And if you do this, you should get as an answer 22 newtons. So this here just becomes 10 newtons plus 12 newtons, and you get 22 newtons. So that's in the horizontal direction, and that's actually the second part of this question, right? The second part of the question is, what is the total horizontal force being applied? So even though this is 20 newtons, only 10 newtons of that is being applied in the x direction. And that 10 newtons can be added with the 12 newtons to figure out that in this direction, you have 22 newtons being applied to the box. So that answers the second part. Now, again, for the first part, we want to find out the total resultant force. So that means we need both of our components. So that was our x. We'll also do the y. And for this case, I'll say up is positive. And again, in some cases, it might make sense to say that down is positive. In this case, you could argue that, but it's completely up to you because when we get our final answer, we're going to indicate the direction along with it. In fact, for the horizontal one, we should say it's 22 newtons to the right, right? We should indicate that direction along with our answer. Now, again, for the y components, for the first one, we can simply say 20 sine 60 degrees. That'll give us this vertical component of the vector. And for the second vector here, remember, 0% of this is actually being applied vertically. It's all being applied horizontally. So you could add 0 here, but you really don't have to, right? You don't even have to include that because nothing from that vector is contributing in the vertical direction. So let's just figure this out. And if you do this, you get 17.3 newtons. And actually, I forgot to do something here. I said up is positive, right? Which means that this thing I've written down here, the 20 sine 60, should actually be negative, right? Because that vector is going downward, right? And not upward, downward. So this should be a negative value, and this should be negative 17.3 newtons. And because it's negative, that means that I can say my answer is 17.3 newtons down, right? You have that direction of down. So make sure you include that. That's what that negative is telling you. And that's very important, right? These signs are very important because sometimes your vectors will be working against one another. Like in the last example, they can be working in opposite directions. You have to know which ones are positive and which ones are negative. Okay? So this is the y component of our resultant vector. Now, these two answers that we got, remember we have to say what the total resultant force applied was. So we have to combine these two things, right? So what we have is 22 newtons to the right. We have 17.3 newtons downward, okay? We have to combine these two things together to figure out what the resultant force would be, right? It makes a right angle triangle because those are your x and y components. Let's figure out what that magnitude is. Again, you can just use the Pythagorean theorem to figure this out. So if you're going to call this vector r, I would say that the magnitude of vector r is equal to the square root of 22 squared plus 17.3 squared. And if you do that, you should get the answer 27.987. I'm just going to round this to 28 newtons. So the resulting force is 28 newtons. Now, what's the angle we have here, right? Because we have to include that angle. Well, we can use tan to figure it out. Tan of, and I'll call this angle theta. So tan of angle theta is equal to opposite over adjacent. So that means that the angle theta is equal to tan inverse of 17.3 over 22. And if you do that calculation, you should get as an answer 38.18 degrees. And I'm just going to write that as 38 degrees. I'll round it to the nearest degree. So we have our force, right? We have our resulting force. It is 28 newtons. We have the angle here of 38 degrees. So we can combine those two things together. Your resulting vector or resulting force will be 28 newtons. And you could say right 38 degrees down if you want to phrase it that way, right? Because that angle we found, 38 degrees, if you're looking to the right, you then rotate 38 degrees downward, and that gets you to your resulting vector. So if you want to phrase it that way, you absolutely could. You could also say something like 28 newtons, 38 degrees below the horizontal. You could state something like that. It's kind of up to you how you want to phrase it. But both of those, I would say, are fair ways to do it. So if we look at the original question again, remember I predicted that we would have a vector that looks something like this. It goes down and to the right, and that is what we have for our resulting vector, right? That's exactly what we have. So the answer we got, I think, makes a lot of sense, right? So your final answer, 28 newtons, right, 38 degrees down.